4.1, the extreme values of functions. We're going to talk about the definition of an absolute extreme value. Another word for absolute is global. And so the definition of an absolute extreme value is that we're going to let f be a function with domain D. So our domain will be covered by the letter D. And then the function f of c is the absolute maximum value on the domain if and only if f of x is less than or equal to f of c for all x in the domain. So what that means is that every single output f of x, every y value, is less than the particular y value of f of c. What I mean by that is if I had a graph like this, every x value down here, I'll use a different color than green. Every x value, all of these inputs are going to give me a y value that is less than this one. And then an absolute minimum is that all values are larger than that value. So for example, every single value is greater than that purple dot. That means that the purple dot is an absolute minimum and my green dot is an absolute max. Absolute maximums or global maximums are also called extrema. It's just our way of saying they're the extreme value. Okay, so for example 1, we're going to look at the graph of cosine of x on the interval from negative pi over 2 to pi over 2, and then we're going to find the maximum and minimum values and where they occur. Maximum and minimum values are the y coordinates of a point, and where they occur are going to be the x values. So the maximum and minimum values, these are y values, and these are our x coordinates. So the first thing we need to do is graph cosine of x on that interval. So let's look at, here's cosine of x on the interval from negative pi over 2 to pi over 2. So if I look at this, I can look at the different values at which there's a minimum and maximum. So right here, you can see I'm at the minimum value at the pi over 2, and if I play this, you can see it getting larger and larger and larger, and then at a certain point, it goes back down because cosine, as we know, increases from negative pi over 2 to 0, and then decreases from 0 to pi over 2. So your maximum value would be right here where the point is at its highest, and your minimums are going to be right here. And again, we're looking for absolute maximum and absolute minimum, so we're looking for the highest and lowest y values. So if we look at our graph, you can see that right here and right here we have minimums, and then we have right here a maximum. So for maximum minimums, again, we're going to look at the y values. So for our graph, we have a max of 1 at x equals 0. And we have a min of 0 at x equals negative pi over 2 and x equals pi over 2. So we have a minimum at 2 points, which is perfectly fine. And right here we have pi over 2 comma 0, and our maximum was 0 comma 1. So that tells us that we have a maximum at 0, 1, and then minimums at negative pi over 2 and pi over 2, which is 0. So I want you to try the same thing, except now try it with negative pi over 2 to pi over 2 with sine of x. So instead of using cosine, we're going to use sine. So take a minute, pause the video, draw sine of x, restrict the domain, and then find the maximum and minimum for that function. Okay, so we're going to look now at sine of x. So here's sine of x from negative pi over 2 to pi over 2. So if I let this graph, you can see that it goes up. Let's start it from the beginning. You can see that sine of x goes up, 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 and continues going up until you get all the way to pi over 2, and then it goes back down. So if we look at it like anywhere, you can see you can get a little bit larger. So let's look at the whole graph right now, and you can see if I zoom in a lot, the idea is that right here I can keep getting larger, and I keep getting larger, and I keep getting larger until I reach here, which is the highest point. Now I know this looks like the same as this, but if we zoom in enough, you can see it start to separate, and it get larger and larger until it reaches its maximum value. Okay, so here's our graph. And you can see right here we have a max of 1 at x equals pi over 2, and we have a min of negative 1 at x equals negative pi over 2. Alright, on to example 2. Exploring the absolute extrema. So we're going to talk about the same function y equals x squared, but in different scenarios. So for y equals x squared, the domain for this graph, we're going to make the domain be negative infinity to infinity. That means there's no restrictions on the graph y equals x squared. Well, we all know that the range from y equals x squared is 0 to infinity. So we don't have a max. What we do have is a minimum value. And the minimum is 0 at x equals 0. So when x equals 0 right here, you have a min of 0. Okay, we're going to look at the same graph, y equals x squared, but this time I'm going to restrict the domain from 0 to 2. I'm using brackets, so I'm going to include the endpoints. I'm going to include these endpoints. So what I want you to do right now is try to determine the max and the min of this function on the restricted domain. Okay? So the max is 4 at x equals 2, and the min is 0 at x equals 0. This happens because this point right here is bigger than the y value, is larger than every other point on this graph. And the same thing for the minimum. This right here is smaller than every other point on the graph. Okay, let's try another one. This time I'm going to restrict my domain to 0, 2, but this time not include 0. So what I want you to do now is try to find the maximum and minimum if there are any. Okay, so we have a max of 4 at x equals 2 again, but this time we have no minimum value. We don't have a minimum because right here I can zoom in over and over and never actually get to 0. Let me show you what I mean by that. So if I look here, I have a restricted domain, and you can see I go down. Now if I zoom in, I can get closer and closer to this value, but never actually get to 0. So 0, 0 is right there, which we're not actually going to get to, but let me plot a point so I can show you what I'm talking about. Okay, so now I can zoom out, and you see that it's the curve, but as I zoom in, I can get closer and closer, but I can never actually get to the point where this point is going to be a little bit smaller than that point. And if I zoom in further, this point is a little bit smaller than that point. And for that reason, we don't have an absolute minimum if the minimum was the endpoint. Okay, we'll try another one. But this time I'm going to restrict my domain from 0 to 2 and not include the endpoints. So here we have no maximum and no minimum. Okay, moving along to the extreme value theorem, the EVT. The extreme value says that if a function f is continuous on a closed interval AB, then f has both a minimum value and a maximum value on the interval. What I mean by that is if I'm on a closed interval, I can definitely have a maximum and a minimum because it's either going to be the endpoints or somewhere in between. Okay, so now we're going to talk about extreme values in their local setting. So you have a local extreme value if f of c is greater than or less than all of f of x on a specific interval. What this means is that I can shrink down the interval to just a section of the graph and find a local min or local max. So a local max at c, if and only if f of x is less than or equal to f of c for all x in some open interval. That means that the y value at a point is larger than all the other y values within a certain interval that I'm going to pick. A local minimum is at c if and only if f of x is greater than or equal to f of c for all x in some open interval. This means that the y value at c is less than all other y values on a specific interval. So let me show you what I'm talking about. Let's look at this right here. Let this be an example. So I'm going to identify all my local maxes. So I have a local max here because I'm going to restrict the domain from here to here. And on that interval, what I dotted was the largest one. So this is the local max. Now I'm going to take an interval and I'm going to say let's look at from here to here. So this point is bigger than all of these y values. So this is also a local max. I'm going to do that again. I'm going to restrict my interval from here to here. So this would also be a local max. Now I'm going to do the same thing with minimums. I'm going to restrict the interval from here to here. So this is a local min. Let's restrict it from here to here. And we get a local min. And I'm just going to use the interval that I created before from here to here. So from right here to right here. And you get another local min. So a local max and a local min, you're basically going to look for where the graph goes up and then down for a max, or down to up for a min. Now, there's one more thing I need to point out, which is you can have a global max, which is the highest point on the entire graph, which would in fact also be this point right here. So this is a local max, but it is also a global max, or a global extrema. This point right here is the global min, because it's the lowest point on the entire graph. So a graph can have, or a point can be a global max and a global min, but it will only have one of those per graph. There's also the possibility of there being no global min or no global max depending on the endpoints. By the extreme value theorem, if it's a closed interval, we know we're guaranteed to get those. Local extrema are also called relative extrema. So relatively to a portion on the graph, they would be the largest or smallest value.